Okay, so hello, this is the next video on the Additional Maths series, and this one is about interception problems. So the last video was about relative velocity, one of the most difficult topics. This one is included in relative velocity, but it's a slightly different type of question. Generally it's a bit easier as long as you understand it. So this is not going to take quite so long as the last video, which was about an hour long. This one should be quite a bit shorter than that. I'm going to explain the basic idea quite briefly. I'm going to explain something about the method that I prefer, because there really are two different ways to do these questions. So I'm going to show you the way that I like to do them, but I will mention the other way. And you'll see that because we're going to do two exam questions. So that's the setup. So let's start with the idea. First of all, the word interception means so intercept. You should remember this word from studying graphs. If you have a graph can have intercepts. So the points that I'm marking out here, the points where the curve cuts the y and the x axes, so I'll mark them in red. This point here and this point here are the intercepts. So it's PT, intercept, not intersect. Yeah, intersect is a similar idea, almost the same to be honest, but intersect and intercept are both referring to the idea, whether it be a graph or an object crossing another object or line. So if you imagined two people walking, one person is walking along this path and another person is walking in a different direction along this path, the lines of their paths may cross. But it's interesting to think, would those two people intercept each other? So think about intercept meaning meet. If I want to meet you and we're both walking somewhere in the city, our interception will be where we meet. We might literally hit each other. Yeah. So will we meet? Yes or no? I hope you understand, or I hope you it's obvious, but I hope you can see that we won't always intercept or meet just because our paths cross. Because, for example, this person may walk very quickly and get here in 1 minute, whereas this person may be walking very slowly and maybe after 1 minute they're only here. So the question of whether two people or two objects intercept or meet does not only depend on the path that they travel, but also on the timing. Yeah. So interception means same place at same time. And this is going to be very important, because in order to solve interception problems you have to use the fact that you have the same time and the same place. So in a way you have two bits of information, not one. Okay, so how does this work using the concepts of relative velocity and the vector concepts that we've already learned? So I prefer to approach these problems in this way. I start from the principle that distance is always velocity times time, or distance is always speed times time, let's say. But using a vector notation, we should use a vector equation there instead, and we should write something like displacement vector, S, displacement, is equal to the velocity vector times time. Now be careful, notice this is a vector equation in which one vector, the velocity, is multiplied by a scalar. Yeah? So you could imagine, for example, a vector equation like this: 3, 9 equals 1, 3 times 3. That would be an example of a vector equation in which the right hand side is multiplied by excuse these little dots here, in which the right hand side is multiplied by a scalar. The 3 is a scalar and the vectors, and of course that's logical. Now that kind of equation is a bit too simple for what we want, what we need. Now, in the picture I drew here of the people walking, of course, the people were walking along curved paths. Now, that will be a bit too complicated for what we're doing today. So, all the motion that we're going to look at will be motion along straight lines. Yeah. So, I'll draw now two straight line paths. And the question of people intercepting or meeting each other will be solved by considering these paths as vectors, yeah, as displacement vectors. So let's suppose that the origin is here. Then each person, let's call them A and B, has their own position when time is 0. Yeah. So at t equals 0, we have the positions here and here. And those positions, of course, are not the position vectors of A and B at time 0 are not 0. They are, if I just draw them, that's the position vector of A at time 0, and we might write that as S 0A. It's a bit of a weird notation, but that will do. And then there's another line, it's a bit of a messy one here, but there's another position vector there, which is the position of B at time 0. So as time progresses, the two people are going to start moving at an appropriate speed along these paths. Yeah, we assume that they each have a constant velocity, and we call those constant velocities, let's say, VB and VA, so that after each second the positions of A and B, these blue arrows, these position vectors, are moving by an amount equal to VA, well, times 1, because after each second they will move by 1 unit of VA and VB respectively. So how does all that look as an equation, and how can that equation help us to find out whether there is an interception at this point or not? Well, we should write it something like this, in the same way that we write, how can I write that? Well, I'll just write it, you'll see what I mean. The position vector of A as a function of time, because as time progresses A will move along his path, will be S0A, which we've already identified as the position vector of A at the beginning, plus the velocity of A multiplied by time. And the position vector of B has exactly the same structure. As a function of time, remember, it's a velocity vector, it's a displacement vector which is changing with time, is equal to the initial displacement vector plus the velocity of B multiplied by time. So that looks a bit complicated if you're not used to this kind of working. Let me just move this out of the way so it doesn't distract us. That looks a bit complicated, but of course, what did we say? We said that interception, a meeting, happens if we get the same place at the same time. That's the key concept there. Yeah. So that means what we need to do is combine these and say, in what situation will SA and SB have the same value at a single time? Yeah. So we can treat this as two simultaneous equations. And the point is, because it's a simultaneous equation, what we're saying is that the value of t needs to be the same in both cases, and then that will allow us to work out various things. For example, we might know VB but not know VA, or we might know the initial position of B but we might not know the initial position of A. And because it's two equations, it will allow us to get two pieces of information. But be careful, each vector, yeah, in 2 dimensions, a vector is like this, x, y, in column form. So it's 2 bits of information. But these 2 equations will be enough to find 2 bits of information. Okay, so in a moment I'm going to show you how you can use this structure to solve interception problems easily. But I must mention that the way I'm going to show you, which is really to write these 2 equations and solve them, it's also possible to take another approach, which is to draw a displacement triangle. So for example, it might be, so in the example of this diagram here, it would be, starting point for A, starting point for B, and draw the displacement vectors the displacement vectors of. So this would this one here would be the displacement vector for A from the start to the end. This would be the displacement vector of B from the start to the end, and this would be the initial displacement between A and B. And if you know the velocity of the objects A and B, the people A and B, you can then use that information to build a triangle and use either the cosine rule or the sine rule to solve the problem. Now I have to emphasize that both the textbook and in some case the exam marking schemes focus more on that geometrical method. Let's say that's the geometrical method. They tend to focus on this geometrical method of using a displacement triangle. Just as when we studied relative velocity examples in the last video, we used velocity triangles, in other words triangles of velocity vectors. Here we can use triangles of displacement vectors to solve the problem. We need to use displacement here because we're interested not just in how fast things are travelling but whether they meet. Yeah. But the method I'm going to show you is what we might call the vector method. Here. Yeah. So the vector method says that if we meet, if there is interception, then we know that SA, the displacement of one of the objects, at a certain time t is equal to SB at the same time t. So maybe I could emphasize by saying at one particular time these are equal. So you're setting this line S0A plus VAT equal to S0B plus VBT with the same t, and you can deduce whatever you need to deduce. Okay, so that's the idea. I hope it's fairly clear what I mean, but it will be much clearer once I've shown you an example. So here's my first example. This is, I think, from 2003 exam, and I don't think it's a very difficult one, but anyway, I guess it's a fairly normal question. So let's read it. An ocean liner, so the word liner here is actually a type of boat, a very large boat, but I guess it doesn't matter if you don't know what it means, is travelling, and it gives the speed and it gives the bearing. Remember, bearing tells us the angle from north. So if this is north, 90-degree bearing is actually due east. Yeah, because that's 90 degrees clockwise from north. So the ocean liner is travelling due east actually, and at a certain time the liner, which is at a 90-kilometer distance from a lifeboat, so that's another object. So we've got the liner and the lifeboat, and the liner is on a bearing of 315 degrees from the lifeboat. Now I want to explain what that means as a picture, because I think a lot of students are going to find this difficult to draw a picture. Actually, you don't need to, but we'll see that in a minute. So if you wanted to, here's the liner. Let's make it really clear. The liner, and here is the maybe a bit further. Here is the lifeboat over here. That's not very good. Never mind. Lifeboat over here. Now if the liner is on a 315-degree bearing from the lifeboat, it means that if we take the north direction from the lifeboat, then the angle all the way around there is 315 degrees, which of course means that this angle is 45 degrees. Yeah? So that's what they intend you to understand from that sentence. Alright. The liner sends a message for assistance, whatever. The lifeboat sets off, so starts moving immediately and travels in a straight line at a constant speed, intercepting, so interception problem, the liner at 0730 hours. Find the speed of the lifeboat. So if you've never studied these problems, you might be very confused because doesn't seem to be telling you anything about what the direction the lifeboat is travelling in. You know it's going to be a straight line, obviously that's important, but they're not giving you the direction. And because I'm going to use this vector method that I mentioned up here, I'm actually not going to need to calculate anything about the angle of the lifeboat. I will just, well, let's say I won't need to calculate it explicitly. It will come out of the calculation, of course. So I'm not going to draw a triangle as the examples in the book will. I'm just going to use this method here. So first of all, I'm going to define two objects. So I've got I'm going to use L for liner, and I'm going to use B for lifeboat because they're both L, which is annoying. And so let's make a quick inventory, a quick list of what we already know. What do we already know? First of all, the velocity of the liner has magnitude 36 in units kilometers per hour. Let's be careful about that. And we know its direction is due east. The what else do we know? The time taken for the whole journey in hours is 3/2, measured in hours. Yeah, so we're using consistent units. And what else? Yeah, we know the direction and magnitude of the liner's velocity. What else do we need? Oh yeah, we know the relative position. Yeah, we know the relative position of the liner and the lifeboat at the start. We know that this distance at the beginning is 90 kilometers. Okay, so that's what we know. So what does the vector method, how does the vector method approach this? It says, well, the displacement vector of the liner at a certain time t will be equal to the displacement vector of the lifeboat at the same time t. That's the key idea. Now, to make everything clear, we need to define a coordinate system. This is a bit messy, but I'll try and do it. So I'll say this is the j vector. A unit vector in the north direction is j, and a unit vector in the east direction is I. Then let's ask ourselves, well, let's expand this. So S, the starting position of the liner, plus the velocity of the liner times t, must be equal to the starting position of the lifeboat plus the velocity of the lifeboat times t. So here t is a scalar and the others are vectors, so make sure you make that clear. Now, if we define, and the most natural way to do it is to define the origin to be where the lifeboat starts. We could define the liner's position to be the origin, but I prefer to do it this way. It's up to you. So having made that choice and having defined I and j, I can rewrite all these vectors in terms of I and j. Do you see that? So the starting position of the liner is here. Now that is at a distance 90 from the origin, and this angle is 45. So it shouldn't take you very long to figure out that if I write that as a column vector, I'm going to get minus 90 over root 2 as the I component, and plus 90 over root 2 as the j component, because that's a 45-degree angle. So that's the starting position of the liner up here. The velocity of the liner is already given, which is nice. We're told that it's 36 magnitude, but it's due east. Well, due east is just I, so it's 36 I component and 0 j component, and that's multiplied by t, and that must be equal to the starting position of the lifeboat, which is actually a 0 vector, conveniently, because it's at the origin when it starts, plus the velocity of the lifeboat, which we don't know. Yeah? So we'll just call it VBX VBY times t. And the good thing is, of course, that we actually do know t. T is 3/2. Okay, so if t is 3/2, we could write all this. Now, it doesn't matter if you use column vectors or IJ notation; it's all the same thing. Excuse me while I just move this out the way. I need more space, so whoops. Why doesn't that move? Ah, there we go. Okay. So it doesn't matter if we use IJ notation or column vector notation. It's the same thing. You can see you know the value of t. You know these numbers, these numbers. The only things you don't know are these two numbers here. So I can just simply write the column vector VBX, VBY. I think I'll change back to black here. So VBX, VBY, basically the vector VB, multiplied by 3/2, which is the time, is equal to minus 90 over root 2 plus 36 times 3/2. You see there I'm adding the I components on the left hand side, and the J component is just 90 over root 2. Okay, so here we could, for example, just it doesn't really matter how we do it, multiply both sides by 2/3 or something like that, and we're just going to get a certain set of numbers for I and a certain set of numbers of J for J. Now I'll skip the actual calculation. I hope it's obvious to you that I can simply calculate the magnitude of this vector. What I'm looking for, according to the question, is just to find the speed. Yeah? To find the speed, I just need the magnitude of this vector. That means I need to take the square root of the sum of the squares of these two components. Very simple. Obviously you need a calculator, but it's very simple. Now here's something very important I want to emphasize. I use this method because I know that this method, this vector method of making the two displacement vectors equal, must always work. And in fact in this case, although the numbers down here are a bit horrible, the actual process is remarkably easy. I mean, I've written all this to make it obvious what's going on, but actually when I first did this question I was able to do it just in literally, I guess, seconds. It's very simple. But here's the really interesting thing. Actually, in the exam, in the mark scheme, the answers given by the examiners, they pretty much expect a student to use a triangle, which it's not a bad method, but it's clear that this method is also very good. So the triangle method here would be to do something like this. Draw a side of length 90, then draw this unknown length. You know the direction here is such that this angle is 45, and you know the third leg of the triangle would be the speed of the lifeboat times 3/2, and the length of this side would be the speed of the liner times 3/2. Yeah. And so you know this angle, and you know this side and this side, so you can use a cosine rule. So clearly it's an absolutely correct method, and maybe they're both pretty quick at solving the problem, but be aware that there are these two different ways to approach these problems. Okay, let's have a quick look at the second example. I think I'll just move it up somewhere here. Oops. I'm in trouble today. There we go. Okay, so this is the second example, and this is a bit unusual that they actually draw a diagram and they give I and J, so they're kind of telling you that they want you to use an IJ method to solve this problem. But like all the other problems, you can either use IJ or use a vector method or a geometrical method. It's up to you. Okay, so let's read it carefully. There's a lot of information here. We've got the diagram showing a horizontal rectangular surface. One corner of the surface is taken as the origin, I and J unit vectors along the edges. A fly starts at a certain point, 112, and crawls across the surface with a velocity of 3.2, so 3i, 2j. At the instant the fly starts crawling, this is important, yeah, because it means the time is the same. When the fly starts crawling, the spider with a different position vector sets off across the surface with a different velocity, and here k is not known. The spider catches the fly. What does that tell us? The spider catches the fly means interception. yeah, or meeting. We need to find the value of k. So this problem is tailor-made for the method that I've just taught you, okay, because here we can say that let's use S for spider and F for fly. Oh, that's actually given in the question, sorry. So at a certain time t, the displacement vector of the spider is the same as the displacement vector of the fly. Yeah. So again, S 0s, the displacement vector of the spider at time 0 plus the velocity of the spider times time, a certain time, is equal to the displacement vector of the fly at time 0 plus the velocity of the fly times time. Same basic idea, you see. And you simply replace these vectors with the data we're given up here. So let's use column vectors because it's quicker. Start of fly is 112 and velocity of fly is 3.2. That's the right hand side. For the spider we've got 85.5 for the starting position, velocity -5 and k times t. So how many equations is this? Yeah, it's a recurring theme, isn't it? This is not one equation, two equations. It's two equations because both the I must be equal and the j must be equal. So two equations is okay because we have two unknowns, k and t. We just simply find them both. Yeah. So let's look at the first equation. For I, we get 85 minus 5t equals 1 plus 3t. This gives me 8t equals 84, which gives me t is 10.5, or let's say 21 over 2. And that's looking at the I components. Now looking at the j components, I'm getting 5 plus kt equals 12 plus 2t. So 5 plus 5 plus 21 over 2 k equals 33, so therefore k is 28 times 2 over 21, which is 56 over 21, which is 8 sevens over 3 sevens, so it's 8 over 3. So the value of k is 8 over 3, and that's the answer to the question. Okay, so that's basically it. There's not much more to say about these problems. Make sure you understand the concept. I recommend the vector method, but you may also want to spend some time looking at the examples in the book. There are some quite difficult examples, and certainly I feel that in the more difficult cases using a triangle can be quite confusing, because sometimes it's not obvious what the triangle should look like. In particular, it's not obvious whether the angles should be obtuse or acute. So that's why I personally always prefer to use a vector method, which allows me to just work from components, like as I did here. I just found the components of the vectors and then found magnitude if necessary. Anyway, I hope that's useful. The next video will be about permutations and combinations. After that, I'm not sure if I'll do any more videos. It depends what's necessary, really. If anybody needs me to do videos on, for example, sets and matrices, I think those are the only other topics which might be necessary. So thank you very much, and see you next time.